Maximum power point tracking using intelligent controller for solar photovoltaic systems. 1. Introduction. 2. Photovoltaic system modeling. 3. Model of the photovoltaic module. 4. Characteristics of a system photovoltaic. 5. Association of the chopper booster and maximum power point tracking. 6. Fuzzy logic controller for maximum power point tracking. 7. Simulation results. 8. Conclusion. Abstract. To reduce environment-related risks and to meet future energy needs, the transition to renewable energy exploitation and technology development became indispensable. Algeria holds one of the highest solar reservoirs in the world for these reasons. The solar photovoltaic arrays are considered one of the most attractive and a significant renewable energy resources. The energy converted directly from sunlight through photovoltaic panel is not steady due to different solar intensity, and maximum power point tracking is used to extract maximum power from the photovoltaic panel. The perturbation and observation algorithm is the traditional solution for MPPT controllers, but perturbation and observation control presented the well-known oscillations, mainly in the sudden changes of irradiance. This paper proposes an intelligent control method for the maximum power point tracking of a photovoltaic system under variable temperature and isolation conditions. The intelligent control uses a fuzzy logic controller applied to a DC-DC converter device. Results of this simulation are compared to those obtained by the perturbation and observation controller. 1. Introduction. The solar energy is directly converted into electrical energy by solar PV module. Each type of PV module has its own specific characteristic corresponding to the surrounding conditions such as irradiation and temperature, and this makes the tracking of maximum power point a complicated problem. 2. Photovoltaic system modeling. The system consists of a PV generator, battery bank, and DC-DC converter. The fuzzy logic-based MPPT control is performed by adjusting the duty ratio of the DC-DC converter. 3. Model of the photovoltaic module. Figure 2 represents the electric model of a solar cell, which consists of an ideal power source connected with a resistance series and a resistance shunt in parallel. Table 1. Module data. 4. Characteristics of a system photovoltaic. Under the conditions of the constant temperature and illumination, the figure 3 represents the characteristic current tension of a cell on this curve. 1 locates the point of no load, CO for I equals 0 ampere, and the point of operation short circuit, ISC for U equals 0 volt. The figure 4 represents the characteristic power according to the tension this curve passes by a maximum of power. Max has this power corresponds a VPM tension and an IPM current, which one can locate on the curve. I equals F V. Influences illumination. For various values of the sunning G1, trace the characteristics I equals F V and variation of the power delivered by the generator according to the tension. See figure 5 and 6, associated with a constant temperature. 5. Association of the chopper booster and maximum power point tracking. So that the module provides its maximum power available, it is necessary to insert a converter booster. Its typical application is to convert its tension of entry into a higher output voltage. The digital maximum power point tracking is based on an algorithm of adaptive control, making it possible to maintain the system at its point of operation of maximum power. 6. Fuzzy logic controller for maximum power point tracking. Fuzzy logic or fuzzy set theory is a new method of controlling the maximum power point tracking. In obtaining the peak power point, typical fuzzy logic-based maximum power point tracking controller includes 3 basic component: fuzzification module, inference engine, and defuzzification module, as shown in figure 12. Inference engine. The inference engine applies the rules to the fuzzy inputs to determine the fuzzy outputs. 7. Simulation results. The simulation is done using MATLAB Simulink. Figure 17. Photovoltaic system with fuzzy logic block diagram. The results of the simulation with the fuzzy logic method. With the method of pi many oscillations, on the other hand, the method of pi. With the method of pi many oscillations, on the other hand, the method of pi. 8. Conclusion. The PV array has a maximum power point which varies with the change of solar irradiation and cell temperature. In this paper, fuzzy logic-based maximum power point tracking controller is developed to identify the MPP, subsequently regulate the PV array to operate at that particular operating voltage. The fuzzy logic controller presented and implemented in MATLAB Simulink environment provides a better response than a conventional perturbation and observation controller in terms of the maximum power tracking performance.